So in the previous video, we saw how the CHSH game could be used as a test for an EPR pair. In this video, we're going to look at another game. It's called the GHZ game, and this game can be used to test tripartite entanglement. So let me show you the game. It's a fun game. There's 3 players now, Alice, Bob, and Charlie. Each of them gets an input, which is just a single bit. X is 0 or 1, Y is 0 or 1, Z is 0 or 1. And they have to produce outputs which are again just a single bit, and for convenience I label these instead of 0, 1 as plus minus 1. So A is plus or minus 1, B is plus or minus 1, C is plus or minus 1. Okay, so what's the condition to win in this game? So the inputs are not going to be chosen uniformly at random. Instead, only 4 out of the 8 possibilities will occur, each with probability a quarter. So with probability a quarter, X, Y, Z are all 0. With probability a quarter, there's a 1, 1, 0, etc. You can see that the parity of these inputs is always 0. And what's the winning condition? The condition is that if all 3 inputs are 0, then the product of the outputs should be plus 1. And in all remaining cases, the product of the inputs should be minus 1. The outputs should be minus 1. So that's the condition. Now, it turns out that if you think about it, classical strategies in this game are not going to do well. In fact, I'll let you compute what is their optimal success probability. Think about it. It's a good exercise. What's the best classical strategy? I'm not going to tell you. Okay, but now there's a quantum strategy that wins in this game not just with higher probability than the classical, but that wins all the time, always gives the correct answer. For that reason, the game is called a pseudo-telepathy game. Let me write it here. The maximum winning probability in this GHZ game is equal to 1. What's an optimal strategy? I'll let you figure it out, but let me give you a couple hints. The state is a state that you've already encountered, the GHZ state. It's this state here. Let me also give you partially the strategy. One part of it is that if either player receives the input 0, what they'll do is that they'll measure in the Hadamard basis. And if they get the outcome plus, the plus state, then they'll answer plus 1. And the minus state, then they'll answer minus 1. Okay, now as an exercise, I'll let you figure out what measurement they should do on input 1. It's going to be the same measurement for each of them, such that they indeed win in the game with probability 1. So it's a convenient game to work with because the success probability being equal to 1 is something that's easier to check. Either the condition should be satisfied all the time, in which case you're doing well, or it's not, in which case you're not doing so well. For a CHSH game, it's a bit more complicated because you should satisfy the condition. Even the best you can is 85% of the time, so in order to check for this, you have to repeat the game many times. But what you can show, I'm not going to show in this video, but it's possible to show using similar arguments that we used in the previous video to analyze CHSH, that this game also has this self-testing property, which is that if a strategy achieves the optimum, then it must be equivalent up to local rotations on Alice, Bob, and Charlie to the strategy that I described on this slide. So the state that they're using must be equivalent to a GHZ state, and the observables that they're using must be equivalent to the Hadamard observable and this other observable that they'll let you determine. And if you want, you can try to show this as a not easy but feasible problem. And the main ingredient I want to remind you, as a first step, you'll use the powerful Jordan's lemma that we saw in the previous video in order to argue that since each player has only 2 possible inputs in this game, then we can assume that their strategy is a qubit strategy. So the entangled state has 1 qubit per player. Once you have this, then you can, get down to the gritty details, start writing down matrices for the observables, and try to figure out conditions on optimal strategies.